Okay, let's just record a couple of simple statements and definitions. So we say a space is simply connected if X is path connected and the fundamental group is trivial. And I've said for X, do I mean for all or for some? Well, they're actually equivalent as long as X is non-empty, because we have assumed path connectedness. Okay. So now if your space is simply connected, you could take this as a definition instead. If I take two paths alpha and beta, we already saw that if they are homotopic fixing endpoints, their endpoints must coincide. But if I have two paths alpha and beta, with alpha of 0 is beta of 0, and alpha of 1 is beta of 1, claim is they are homotopic. Okay. So suppose we have alpha of 0 equals, or maybe I should just say alpha beta, they map 0, 1 to X, and alpha of 0 is beta of 0, alpha of 1 is beta of 1. I'm going to use the fact that the fundamental group is the same for all base points. Then say beta is homotopic to alpha star alpha bar star beta, because this is homotopic to E. Okay, but that is homotopic to so alpha star alpha bar star beta, which is homotopic to alpha star alpha bar star beta. But now this is a loop, so this element belongs to pi 1 of X with coefficients in where it ends, which is beta of 1, which is also equal to alpha of 1, which is alpha bar of 0. Okay, so this is trivial. So this is the trivial group. So this is homotopic to alpha star E, which is alpha. Okay, so that's out of the way. We have a simple fact. Now let's come to our main story. Here we have X. So we had phi, which maps alpha beta to X, well, not to X itself, but pi 1 of X, X0. Okay, which is this curve, and it also has alpha and beta here, alpha and beta. Previously I think beta was oriented the other way, and we have the universal cover X tilde, which branches out, etc. Okay, and previously we defined a path, and now we'll define another path, which we actually mentioned earlier, but we'll have explicit notation. So what we have is the following. So suppose we have W is a word in the usual set, alpha, beta, alpha bar, beta bar, and let's say W is reduced. Sometimes we need W is reduced, sometimes we don't. We previously defined eta W. Okay, so we defined eta W. Okay, but now so eta W maps 0, 1 to X tilde. Okay, now define another map theta W, which we did implicitly. So theta W equals L1 star L2 star Ln if W is the word L1, L2, Ln. Okay, so the main difference here is theta W is a path in 0, 1 to X. So for example, if W was alpha alpha beta, then theta W just goes around this twice and then goes around beta once, while eta W goes around here twice and then goes up to this guy. It's here. Okay, from this description you can immediately see something, right? So remark, eta W, which is theta, we'll write it as theta W, tilde is the lift of W starting at E. Okay, I assume that the parametrization has been done in the same way for the two, simply because if you apply P, you will get a sequence of letters, and eta W had the letter which, so eta W had, so this was E L1 star L1, L1, L2 star etc. star L1 all the way to Ln minus 1 and L1 all the way to Ln, and this maps under the projection map P, projection meaning covering map P, to simply L1 star L2 star so on star Ln, and this Ln is going to be theta W. Okay, so this is the key point. So we now know the lift. So once we have all this, as you would expect, we are set. We want to show this. Okay, so proof. So did I state the theorem? I will state a theorem. Phi from alpha beta to pi 1 of xx0 is an isomorphism. And we'll have another result which we'll get as a corollary of the methods, not of this theorem. Okay, so proof. Let's show injectivity. Okay, so how do we show injectivity? So suppose G is an element in alpha beta. Then we know every element is equivalent, every word is equivalent to a reduced word. So G equals W with W reduced. Okay, so this we know. So if G of phi of G is the identity, then theta, sorry, I didn't observe, I think, one more thing. So what is the relation between phi and theta? Phi of W is the class of theta. This follows simply from the homomorphism property. It's true for each letter, and this is a product of the letters. Okay, this is what we had implicitly earlier. So then theta of W I should say. Oh, sorry, it is theta W. So this one is not really theta of W, but theta W. Oops. Then what we know is theta W is homotopic to identity. So what this implies is theta W tilde 1 is going to be E tilde 1, which is just the base point E. Okay, which is the base point E. But theta W tilde 1 is going to be eta W of 1, because for reduced words this is the case, which is W. Therefore G is W, which is the empty word. Okay, so this is E. So this shows injectivity of the curve. Okay, how about surjectivity? That is similar. So for this we have to pick an element. Let's say let alpha, the class of alpha, belong to pi 1 of xx0. And I have to show this is the image of some word. So I have to identify what the word is. Well, we'll look at the lift of this and see where it ends. Okay, so let alpha tilde, this is going to map 0, 1 to x tilde, be the lift of alpha, starting at the origin E, which is the empty word. Okay, so what is this? So let W, so this is in V tilde, be alpha tilde of 1. So remember alpha tilde of 1. Okay, so W is a reduced word. That we know. Thus, well, alpha tilde of 1 is also eta W tilde of 1. Why is that? That's simply because eta W tilde ends, sorry, this is not tilde here. It's just called eta W, even though it's a tilde. Eta W of 1, okay, but that is theta W tilde of 1. But remember, we saw that as x tilde is simply connected, we saw it's contractible, hence it's simply connected. It's path connected and has trivial fundamental group. Okay, so it follows that eta W is homotopic to alpha tilde. Okay, so this is theta tilde. So this implies that theta W. Alpha, the class of alpha, is the class of theta of W. But that is the same as phi W. Not phi sub W, but phi of W. Done. We have surjectivity as well. And finally, here's the theorem of Nielsen, which we can prove. Okay, as I said, reduced forms, it's not obvious that they're unique, but it's true here in this case. So if W1 and W2 are reduced, by which I mean there's no further cancellation, and they are equivalent to each other under cancellations and uncancellations, then in fact they're equal on the nose as words. So this means these are equal as, so it says that it's, so this says that the class of W1 in the free group is the class of W2 in the free group. Then they're actually equal as words itself. Okay, and the proof is almost immediate from what we have seen so far. Namely, so if W1 equals W2 in the free group, this implies that phi of the class W1 equals phi of the class W2. Okay, that is that theta, the class of theta W1 is homotopic to theta W2. Okay, so this implies that theta W1 tilde of 1 is theta W1 2 tilde of 1. But what is this? This is W1 and this is W2. So we have a nice application to a non-trivial theorem in combinatorial group theory. There will be more non-trivial applications later already from this. Okay, that is the reduced word for a free group is unique.